Take it away, Nick.
Great, thanks so much for having me. So I want to talk about joint work with my colleague Ben Elias and my former student Jane Miata and Lorenzo Becchi, who's now a postdoc in Sweden. Sorry, get this working. All right, so this is just a really quick overview of what I'm going to do. So I'm going to tell you what a valuation is, or valuative invariant for polytopes and matroids. And I want to talk about a few examples, the trivial invariant and Poincare polynomial and Chow polynomial and augmented Chow polynomial. And this is a little orthogonal to the main line of the talk, but I just want to state a theorem and a conjecture about some of these invariants just to motivate why they're interesting. And then I want to do categorical versions of all of this. So I want to say what a categorical valuation is for polytopes or matroids, and then we have sort of categorical lifts of the invariants. And then, I want to state some conjectures about the categorical invariants that categorify the things from the first part of the talk. So let's get started. So suppose I have a real vector space V, and I have a polytope in V, so just a convex hull of a finite set of points. And I want to consider this enormous abelian group with basis given by all polytopes. So it's a very, very infinite rank. And I want to consider the homomorphism from polytopes in V, from this abelian group to functions on V that takes a polytope to its indicator function, 1 on the polytope and 0 outside. And I of V is going to be, by definition, the kernel of that homomorphism. So here's a little example. So this octahedron can be written as the union of this upper tetrahedron and a lower tetrahedron along a square. So if you take the indicator function of the octahedron is equal to the indicator function of the upper tetrahedron minus that of the lower tetrahedron plus that of the square, right? So this alternating sum is an element of I of V. But that's a three-dimensional example. Let me show you a smaller one. It's maybe a little easier to visualize. Here I have a triangle subdivided into 4 smaller triangles. And if I take the big triangle minus the 4 small triangles, that's almost 0 in terms of the indicator functions, but it's not quite right on the edges. And I add the 3 internal edges, then that sums to 0 in terms of the indicator functions. You have to think for a little bit to convince yourself that it's really 0 at all the vertices, but it is. So let's talk about generalizing these 2 examples of elements of I and V. So I want to talk about a decomposition of a polytope. So it's a collection of polytopes such that it's closed under taking faces, it's closed under intersections, and the union is the big polytope. So in this example, P would be the big triangle, and curly Q would consist of the 4 small triangles and all their edges and all their vertices. So elements of this Q are called faces, and a face is internal if it's not contained in the boundary. So here, there are a bunch of non-internal faces, like the exterior edges and all of the vertices. The internal faces are the 4 small triangles and the 3 internal edges. There are no internal vertices in this picture. And a theorem, which I'm attributing to a lot of different people, says that, and I'll talk about that in a second, that for every decomposition like this, you have a class in I of V, which is the big polytope, minus some alternating sum of the interior polytopes, where the signs depend on the dimension, the interior faces. And furthermore, I of V is spanned by elements of this form. So if you combine the work of these first 3 guys, basically they show that, I mean, it's not that hard to show that for any decomposition of a polytope, you get a class in I of V. And that class, the way they wrote it down, is messy with a lot of cancellation. But they proved the hard statement that these classes actually generate I of V. And then much more recently, Ardila, Fink, and Rincon showed that this kind of messy alternating sum simplifies quite a bit. So they wrote it in a way where every face appears only once, and it appears with coefficient 0 if it's not internal. And if it is internal, it appears with coefficient +1 or -1, depending on its dimension. So it's a much nicer form. Okay, so that's a decomposition. So now I want to talk about homomorphism. Sorry, I saw something that somebody put something in the chat, but I didn't see what it was. Is there a question? Okay, so there's also another possible reference. Thank you. Okay, so a homomorphism from Pol V to some abelian group, that's just specified by giving a number to every polytope. Right? And we say that it's a valuation if I of V is contained in the kernel. So by this theorem I just stated, it means for any decomposition, phi of P has to be equal to the alternating sum of phi of Q for the internal faces. That's what it means to be a valuation. The first example I want to give is the trivial homomorphism, or the thing that takes every polytope to 1. I don't want to claim that this is a really hard or deep theorem, but I do claim that it's not completely obvious. So if you get bored over the next 10 minutes or so, maybe just try to come up with a completely elementary proof of this and tell me what it is after the talk. Because, I mean, again, I know how to prove it. And in fact, I'll give you a proof later in the talk. And the proof I'll give will be overkill. And there are easier ways to prove it. But I think it's not completely trivial that if you try to associate the number 1 to every polytope, that this kills elements of I of E. Okay, so let me now restrict my attention to a particular class of polytopes, namely matroid polytopes. I know most of you know what a matroid is. In particular, the definition appeared in the last 2 talks in this series, but I'll just say it again really quickly. So we have a finite set, and we have a collection of subsets called bases. There's at least one basis, and it satisfies this basis exchange axiom. So if you have 2 different bases and an element of the first one, then you can sub it out for an element of the second one and still get a basis. If you are already comfortable with matroids, that maybe sounds fine. If you're not, let's just think about this special case. So we have a vector space, and we have a whole bunch of vectors in the vector space, a finite set of vectors, but they span the entire vector space. And then B, the set of a subset of the vectors is a basis if it's literally a basis for the vector space. So such a matroid is called realizable over C if it's a complex vector space. Okay, so given a matroid, one can come up with.
Sorry to interrupt. Just a clarification about the valuation on polytopes. Usually, valuation of polytope in some of the literature on a polytope is a finitely additive measure.
Okay.
Is it the same?
I don't know. I'm not familiar with that terminology.
Okay, it's just a measure that's valuation of union is valuation of sum of valuations minus valuation of the intersection.
Yes, it is the same then.
It's the same notion, yeah?
Yep.
Okay.
Somehow there are a lot of different notions, and the theorems that I was citing were proving that all these different notions are equivalent. And the references I got were from the appendix of the paper by Ha and Larson, which have a lot of good history of this notion, but it's possible that they left out some other good references. Okay, so for every matroid, I have a polytope. The polytope is in the vector space with basis given by the ground set. So if it's a ground set of size 10, it's in R10. For any subset, I can write down sort of the indicator vector of that subset. So this is a 0, 1 vector that's sort of ones on the subset and zeros outside the subset. And then I can take, in particular, the indicator vectors for the bases, all the bases of my matroid, and then take their convex hull. So that's the polytope associated with a matroid. And I wanted to find mat E to be the subgroup of pol RE generated by matroid polytopes. So I'm not considering all polytopes in R to the E, but just matroid polytopes. And I want to take I of E to be mat E intersect I of RE. This theorem sounds almost tautological, but if you think about it for a second, it's not. It says that IE is generated by elements associated with decompositions of matroid polytopes into matroid polytopes. Right? IE has to do with taking polytopes and breaking them up into smaller pieces. And you can imagine that I could take a matroid polytope and break it up into smaller polytopes, which are not matroid polytopes, and then reassemble them into some different matroid polytope and get some interesting relation between matroid polytopes that don't come from just looking at matroid polytopes. But Dirksen and Fink showed we don't have to worry about that. If you want to understand sort of the valuative relations between matroid polytopes, it's enough to just look at decompositions where everything is a matroid polytope. It's the nice theorem. Okay, now again, a homomorphism from mat E to A is a valuation if I of E is contained in the kernel. So just to be clear, if I have a valuation on all polytopes, then it restricts to a valuation on all matroids. But maybe I have a valuation on matroids that doesn't naturally extend to all polytopes. I want to discuss a few examples of valuations on matroids where the abelian group is polynomials in one variable. So first I want to look at the Ehrlich-Solomon algebra of the matroid. So this is some algebra defined by explicit generators and relations. If you know what it is, that's great. If not, maybe it's good to think about the special case of a complex collection of vectors. I can look at hyperplanes, namely the orthogonal, the perps to the vectors in the dual vector space. And I can take the complement of all those hyperplanes. And then the Ehrlich-Solomon algebra is just the cohomology of the complement. And the Poincare polynomial, it's the generating function for the dimensions of the graded pieces of the Ehrlich-Solomon algebra. In other words, it's the Poincare polynomial of this space U in the realizable case. This is closely related to the characteristic polynomial just by a little change of coordinates. So the characteristic polynomial is the Poincare polynomial, but written backward with signs. People are more familiar with that. And here's my little digression just to sort of motivate the study of this polynomial. So maybe a lot of you are familiar with the theorem of Adiprocito, Ha, and Katz, and it says the coefficients of this polynomial form a log concave sequence. In other words, the coefficient of t to the I, ai squared, is greater than or equal to ai minus 1 times ai plus 1 for all I. So I'm not going to talk about this more, but I'm going to come back to it again when we talk about categorical invariance later. So the Poincare polynomial is a valuative invariant. It's a valuation, or more specifically, the homomorphism from mat E to z of t, taking a matroid to its Poincare polynomial is a valuation. I'm abusing notation a little bit. I should say taking p of m to pi m of t, but I'm sort of conflating a matroid and its polytope inside the group mat E. And I'll also note that Speyer proved something stronger. He proved that the Tut polynomial is valuative, and the Poincare polynomial is an evaluation of the Tut polynomial, so it's also valuative. Now I want to talk about these two other examples, the Chow polynomial and augmented Chow polynomial. So there's something called the Chow ring of M. It's also defined by explicit generators and relations. I'm not going to write down the presentation. But again, in the realizable case, you have this variety U, the complement of the hyperplanes. Sorry, I had a little typo here. What I wanted to do is I want to take U mod C star. So this is sort of the projective complement of the hyperplane. And then you there's something called the wonderful compactification of that. And then CH of M, CH underline of M is the cohomology ring of the wonderful compactification. So it's a compactification of U mod C star.
Nick, maybe you should say with the maximal building set.
With the maximal building set. Yeah.
Thanks.
Fair enough. And the Chow polynomial is just the Poincare polynomial for that. And I'm not going to tell you how to define the augmented wonderful variety, but there's a related ring also defined by generators and relations called the augmented Chow ring. In the realizable case, it's the cohomology ring of something called the augmented wonderful variety, and the augmented Chow polynomial is the Poincare polynomial of that. The only thing that I really want you to notice, if you're not familiar with these polynomials, is the Chow polynomial goes up to the rank of the matroid -1. The rank is the size of a basis. And the augmented Chow polynomial goes up to the rank of the matroid. So it's 1 degree larger. And here's a conjecture about these polynomials. This conjecture, well, various parts are due to various people. So Ferroni, Schroeder, Stevens, and Ferroni, Matherin, Stevens, and Becky. So these polynomials are both supposed to be real rooted, and their roots interlace. So like if one of them is degree 5 and the other is degree 4, their roots fit together like this. Here's the more formal way to say it. You have rank M roots of the bigger polynomial, and rank M -1 roots of the smaller polynomial, and the roots fit together along these inequalities, strict inequalities. So that's an open conjecture. They're not even known to be real rooted. It's conjectured to be real rooted with interlacing roots. And again, I'll come back to this when we talk about the categorical versions. But for now, let me just say that these polynomials are both known to be valuative. And just to make things clear, I'm not claiming that this theorem is going to help us prove this conjecture. But I am claiming that this theorem helped to formulate this conjecture. And the fact that these are valuative makes it easy to do a lot of calculations very quickly. And Luis Ferroni in particular is a wizard at doing these calculations. And he's looked at a lot of data, and that absolutely informed these conjectures. So the relationships between the conjectures that I'm stating and the valuative theorem, I'm not claiming that it will be useful for proving, but it's definitely useful for formulating and checking, testing these conjectures. All right, so what I want to do now is spend some time outlining a proof that the Chow polynomial is valuative. So for this proof, I mean, it's a statement about matroids, but I want to go back to the world of polytopes. So suppose I have a real vector space and I have a linear functional in that vector space, psi. And for any polytope, I want to consider a subpolytope, which is the face on which the linear functional is maximized. It might be a vertex, it might be the entire polytope, it might be something in between. And I want to consider the homomorphism from polytopes in V to polytopes in V that takes every polytope to the face on which this linear functional C is maximized. So McMullen proves that this homomorphism takes I of V to I of V. And let me sort of illustrate this in an example. So let's think again about this decomposition of a big polytope into smaller triangles and edges. And I want to consider the linear functional that sort of measures up and to the right. So it takes it takes A comma B to A plus B. So this P goes to P psi, it takes everything to its northwest facet. So we have this element of I of V, which is P minus the 4 triangles plus the 3 internal edges. And what does it go to when you apply delta psi? Well, when you apply delta psi to P, you get P psi, which is this entire northwest interval. When you apply it to these 4 triangles, this one goes to A, this one goes to B, this one in the middle goes to the vertex F. and this one down in the bottom left goes to the edge G. So that's the ABFG. And when I apply it to the three internal edges, this one goes to F, and this one goes to F, and this one here goes to itself, G. So that's where this comes from. And now you see the three copies of F cancel into one copy of F, and the two copies of G cancel completely, and you just get P psi minus A minus B plus F. And that's exactly the element of I of V coming from this decomposition of P psi here into A, B, and F. So I have an element of I of V given by the decomposition of the big triangle. And when I apply delta psi, I get the element of I of V corresponding to the decomposition of this interval. So McMullen's theorem says that that always happens. Okay, now I want to look at McMullen's theorem and sort of specialize it in the matroidal setting. So suppose I have a ground set E that's the disjoint union of two parts, E1 and E2. So if I have a matroid M1 on E1 and a matroid M2 on E2, I can build a matroid on E. Sometimes this is called the direct sum, but I'm going to use direct sum for something else later. So I'm going to call it the disjoint union. You might know it as the direct sum. And the bases are just unions of bases for M1 and M2. So basis for M1 union M2 is a basis for M1, disjoint union basis for M2. And the polytope for this disjoint union is just the product of the polytopes for M1 and M2. So for example, if I have a bunch of vectors in one vector space and a bunch of vectors in another vector space, then this operation just takes the direct sum of the two vector spaces and takes the first set of vectors, comma 0, and then 0, comma the second set of vectors as my vectors. Okay, so now I want to consider the subgroup of mat E spanned by matroids of this form. So not all matroids on E are of this form. This subgroup is just the tensor product of mat E1 and mat E2, right? So in other words, a basis for mat E1, E2 is given by a matroid on E1 and a matroid on E2. And it's not that hard to show. I mean, this is a non-trivial statement, but not super hard, that if you want to understand decompositions of matroids of this form, it's sufficient to only consider matroids of this form. So somehow every decomposition of a matroid of this form comes from, in some sense, decompositions of matroids on E1, which I just crossed with matroids on E2, and decompositions of matroids on E2, which I just crossed with a matroid on E1. All decompositions of matroids on this form come from decompositions of the two components. So that was about how to take a matroid on E1 and a matroid on E2 and put them together to get a matroid on E1 disjoint union E2. You can go in the other direction. You can start with a matroid on E and construct a matroid on E1 and E2. The matroid on E1, I want to get by deleting the elements of E2, and a matroid on E2, I want to get by contracting E1, or contracting a basis for E1 and deleting the rest. So again, let's just think about what this means in terms of vectors. I can define two new vector spaces. One is the span of the vectors corresponding to the ground set E1, and the other is the quotient by that span of the ambient vector space. And M1 is just given by the vectors V sub E for E and E1, which are all in the vector space V1. And M2 is given by the rest of the vectors, but projected onto the vector space V2. So now a basis for M, so it's not true that M1 disjoint union M2 is my old matroid M, but a basis for M1 disjoint union M2 is a basis for M such that when I intersect with E1, I get a basis for M1, or equivalently, if I intersect with E2, I get a basis for M2. In particular, it's a subset of all the bases for M. And that means that the polytope for M1 disjoint union M2 is contained in the polytope for M. It might be equal, and it usually won't be equal. Okay, so let me consider the linear functional that just takes the sum of the E1 coordinates. Right, so I have an element of R to the E, and it has lots of coordinates, some in E1, some in E2, and I just take the sum of the E1 coordinates. Then I claim that this operation of taking a polytope to the face on which the linear functional is maximized exactly takes my polytope P of M to the subpolytope P of M1 disjoint union M2. So that means that you can think of this delta psi as a homomorphism from mat E to mat E1 tensor mat E2 that takes M to M1 tensor M2. That's exactly the upshot of this lemma. So putting everything together, we get the following construction. So suppose I have a valuation for matroids on E1 and another valuation for matroids on E2. I want to define a new homomorphism that takes a matroid on E and gives a polynomial. And what does it do? It takes the matroid on E and it breaks it up into a matroid on E1 and a matroid on E2. And then it applies phi1 to this part and phi2 to this part, and then takes the product. So more concretely, phi1 star phi2 of M, it's just phi1 of M1 times phi2 of M2. And the theorem of Ardila and Sanchez says that this homomorphism is a valuation. So this is a nice way to make interesting valuations out of smaller, simpler valuations. The proof that they give, which is a very nice proof, doesn't use McMullen's theorem, but I want to outline a proof of this theorem that does use McMullen's theorem. By McMullen's theorem, this delta psi takes I of E to I of E1 tensor mat of E2 plus mat of E1 tensor I of E2 in here. And then phi1 kills I of E1. So phi1 kills this stuff. And phi2 kills this stuff. So if you take phi1 and phi2 and you multiply them together, everything in here dies. So let's tie this back to the theorem about the Chow polynomial. So for a subset of E and a natural number, I want to consider the homomorphism from mat S to Z that takes a matroid to 1 if M has no loops and its rank is K. Sorry, I want to take a matroid on S and take it to 1 if M has no loops and its rank is K, and 0 otherwise. And you can just show completely concretely, in a hands-on way, that this is a valuation. So theorem of Feichner and Uszynski says, well, okay, they didn't state it this way, but they give a nice basis for the Chow ring. And you can use the basis to compute the Poincare polynomial of the Chow ring. And essentially what they're saying is that the Poincare polynomial of the Chow ring, or the homomorphism taking a matroid to the Poincare polynomial of the Chow ring, is a Z of T linear combination of homomorphisms of this form. I mean, really what they're saying, for those of you more familiar with their work, is that there's a basis given by chains of flats, indexed by chains of flats, plus some auxiliary data. Given a chain of flat, you get a few different basis elements in various different degrees. And when I convolve these things together, I get a homomorphism that basically asks me if S1 union S2, S1 union S2 union S3, ... is a chain of flats of these particular ranks. So for every chain of flats, I get a 1, and then I take some Z of T linear combination depending on the ranks, and that's going to give me the Poincare polynomial. So by the theorem of Ardila and Sanchez, this homomorphism is a valuation, and you can do something similar for the augmented Chow polynomial, the augmented Chow ring. So that's one way to prove that these guys are both valuative invariants. Okay, quick recap. So the Poincare polynomial, the Chow polynomial, one of these was supposed to have an underline. The Chow polynomial and the augmented Chow polynomial are all valuative invariants of matroids. That makes it easy to compute for large classes of matroids, which is great. But I still regard the valuativity condition as somewhat mysterious and the proofs as opaque, and it's a little hard to tell what's going on. Yeah, Nir, do you have a question?
Yeah, if you have a valuative invariant, is it determined by what it does in realizable matroids?
Yes. Yes, it is.
Okay. Thanks.
Yeah, the valuative group is spanned by classes of realizable matroids. So to try to demystify this a little bit, I want to go back to trying to understand the trivial homomorphism, the thing that takes every polytope to 1. And I want to understand why it's a valuation. Again, here I'm going to give you one proof for why it's a valuation. So suppose I have a decomposition of a polytope P, and I choose an orientation of every face. I can think of this decomposition as a cell complex where the total space is P and the faces of the cells. And then I have a cellular chain complex for the cell complex. I've got here the 0 cells and the 1 cells all the way up to the dim P dimensional cells. And now I want to kill all the things corresponding to non-interior faces, the boundary faces. So now it's not going to be a cell complex for P, it's going to be a cell complex for P relative to the boundary of P. And it's going to look like this. So remember, Q0, that's not the zero-dimensional faces, that's the zero-dimensional interior faces. And Q1 is the one-dimensional interior faces. So the homology of this complex is going to be equal to the homology of the pair P comma boundary of P, which is one-dimensional and concentrated in top degree. I can build a complex with zero homology by just adding one more copy of Q in the beginning, like that. So this thing is going to be exact now. And well, since it's exact, the Euler characteristic is 0, so I can take the alternating sum of the dimensions. So that's 1 for this, and the number of p-dimensional faces for this, and the number of p-1 dimensional faces for this, yada, yada. That's just tau of p minus alternating sum of tau of q's. So that's exactly the statement that tau vanishes on the generator of I of v corresponding to q. Right, so this is maybe an unnecessarily highfalutin proof that the trivial invariant is a valuative invariant, is a valuation. But maybe really helps you understand what's going on, why it should be a valuation. So yeah, so building on this perspective, I want to consider now a category where the objects are polytopes in V. Or really, I want it to be an additive category. So the objects are given by formally taking direct sums of polytopes in V. And what is a homomorphism from one polytope to another polytope? Well, I want to say that I want it to be a Q-linear category. So the homomorphism is going to be a Q vector space. And if P prime is contained in P, then I want there to be a one-dimensional space of homomorphisms from P to P prime. So there's sort of a distinguished one, which I'm going to call iota P, P prime. And if P prime is not contained in V, I want to have no homomorphisms from P to P prime. So given a decomposition of a polytope P, where I've chosen orientations of all the faces, I can build a complex in this category where, just in rank K, I have all the sum of all the K-dimensional interior faces. And the point is, if I want a map from a 5-dimensional face to a 4-dimensional face, well, maybe that 4-dimensional face is contained in the 5-dimensional face, and then I want to take sort of iota, or maybe it's not, in which case I have 0. And then I have to have some signs depending on the orientations. Does the orientation of the bigger thing induce the orientation of the smaller thing on the boundary or not? And I also have a P here because all these Q's sit inside of P. I get a complex like that. Now suppose I have an abelian category. If I have a functor from my category of polytopes to the abelian category, I want to say that it's a categorical valuation if it takes this complex for any decomposition to an exact sequence. And let me just note that if I have a functor between these two categories, then I have a homomorphism between their Grothendieck groups. And the Grothendieck group of this category is just Pol V, and the Grothendieck group of this category is some abelian group A. And saying that this functor is a categorical valuation implies that the map on Grothendieck groups is an ordinary valuation. And the example, we've sort of already done the main example, or the first example I want to talk about. It's the trivial functor that takes every polytope to the vector space Q and every inclusion of polytopes to the identity map from Q to Q. This is a categorical valuation. It categorifies the trivial valuation. And that's exactly this observation about that sequence being exact. So I want to do something similar for matroids. So I want to define curly M of E to be the subcategory generated by matroid polytopes. And similarly, a functor from that subcategory to A is a categorical valuation if it takes the complex associated with a decomposition of matroid polytopes to an exact sequence, split exact sequence. Okay. I guess maybe I've been a little inconsistent in these slides about whether I want A to be an abelian category or an additive category. If you care a lot about these things, I'm happy to talk to you about it later. Otherwise, assume whatever context you're more comfortable with. So an example of a functor of this type is the Orlick-Solomon algebra. So I didn't give you the definition of Orlick-Solomon algebras in terms of generators and relations. But if I did, it would be clear that if you had two matroids, M and M prime, if the matroid polytope for M prime is contained in the matroid polytope for M, then the Orlick-Solomon algebra for M prime is actually a quotient of the Orlick-Solomon algebra for M. So that means that if I have a morphism in my category from M to M prime, then I get a map of Orlick-Solomon algebras from OS of M to OS of M prime. So it's a functor, and it categorifies the Poincare polynomial. So with Ben Elias, Dane Miata, and Lorenzo Vecchi, we proved that this is a categorical valuation. In other words, whenever I have a decomposition of matroid polytopes into smaller matroid polytopes, I actually get an exact sequence on Orlick-Solomon algebras. And we also do similar things for the Chow ring, the Chow polynomial and augmented Chow polynomial. So the Chow polynomial is the Poincare polynomial of the Chow ring, and the augmented Chow polynomial is the Poincare polynomial of the augmented Chow ring. So we show that whenever you have what's called a weak map of matroids, whenever you have P of M prime contained in P of M, you get a map from the Chow ring for M to the Chow ring for M prime. It's not going to be a ring homomorphism. It's just going to be a map of vector spaces, map of graded vector spaces. That's okay. And similarly for augmented Chow rings. And they have the property that when you evaluate on a complex corresponding to a decomposition of matroid polytopes into smaller matroid polytopes, then it actually gives you an exact sequence. So this provides sort of some explanation for why the polynomials are valuative. I want to talk a little bit about the proofs of these statements. So the proof of the first statement about the valuativity of the Orlick-Solomon algebra, it's not trivial, but it sort of has the same flavor of the proof that the trivial functor is a categorical valuation. So, you sort of pick out a piece of the Orlick-Solomon algebra, and then you you get some complex and you show that that complex is computing the homology of something, and you show that the homology vanishes. So it has a similar topological flavor. I won't go through the details. But I do want to talk about the proof that the Chow polynomial and augmented Chow, sorry, the Chow ring and augmented Chow ring are valuative functors. And for that, just like the key step in the non-categorical setting was Macmillan's theorem, the key step here is a categorical analog of Macmillan's theorem. So let me state it. So V is a real vector space, and I have a linear functional. Again, I have P psi as the face of P on which psi is maximized. And I want to define a functor from the category P of V to the category P of V. It takes a polytope to P sub psi, to the face on which psi is maximized. If P prime is contained in P, then it may be that P prime psi is contained in P psi, and it may be that it isn't. So if it is, then I just take sort of the distinguished map from P to P prime to the distinguished map from P psi to P prime psi. And if it's not, well, there's nothing I can do. I have to take it to 0, right? If P prime psi is not contained in P psi, then there are no maps in my category from P psi to P prime psi, no non-zero maps. So I have to take this thing to 0. So that's my functor. And then the theorem is that if Q is a decomposition of P, then I can look at the induced decomposition of P psi, just as we did before. And my functor will take the complex associated with Q, not to the complex associated with Q psi, but to a shift of that up to homotopy, which is good enough for Macmillan's theorem. So let's look at this example again. So I have the complex associated with the big triangle. So I have P, which goes to P psi. Then I have 4 two-dimensional things, one of which goes to A. This one goes to A. This one here goes to F. This one here goes to B. And this one here goes to G. And then I have 3 one-dimensional things. This one here goes to F. This one here goes to F. And this one here goes to G. So I get a new complex like this. And then what happens? So up to homotopy, this thing is null homotopic, so this can just be canceled. And it's also possible to cancel sort of 2 of these copies of F. So I can write a new complex that's homotopic to this complex, where these 2 copies of F die, and now this A goes to this copy of F, and the whole thing is homotopy equivalent to C to the complex associated with Q psi, but now shifted 1 degree to the left. Okay, so this is an example which illustrates the categorical analog of Macmillan's theorem. So then once you prove Macmillan's theorem, you can use that to prove valuativity of the Chow ring and augmented Chow ring. So what I want to end with is saying sort of, so what? So I sort of have 2 justifications that I want to give for doing all of this. One is, I think it makes the notion of valuations a little less mysterious. You have this alternating sum of polynomials that's supposed to equal 0, and that's strange. But if you're told, well, these polynomials are actually Poincare polynomials of graded vector spaces, and you have a canonical exact sequence on those graded vector spaces, that's somehow less strange, and maybe telling you what's really going on. So that's one reason. But the other reason is that you can do more with categorical valuations than with the ordinary ones. So not all, but some of them, including the Ehrlich-Solomon algebra, the Chow polynomial, the augmented Chow polynomial, are functorial not only with respect to inclusions of matroid polytopes, but also with respect to permutations of the ground set. So like if I have a matroid on E and I have a permutation of E that preserves the matroid, that preserves the set of bases, I actually get an automorphism of my Ehrlich-Solomon algebra. and similarly for Chow rings and augmented Chow rings. So really what that means is I can look at this, let's say this exact sequence of Orlick-Solomon algebras associated with a decomposition. And if I have some finite group that acts on the ground set by permutations and preserves the decomposition, then all the things that appear in that exact sequence will actually be representations of gamma. And I get an exact sequence of representations, of graded representations of gamma, rather than just of vector spaces. So I can use it to compute these Orlick-Solomon algebras, not just as vector spaces, but as representations of my group. And similarly for the Chow ring and augmented Chow ring and many other categorical valuations. And I just want to point out that these are much richer invariants than the polynomials. So when I think of my Orlick-Solomon algebra, if I just remember the dimensions of the graded pieces, that's one thing. But if I remember what the graded pieces are as representations of my automorphism group, that's a much richer invariant. So just to illustrate some questions we might ask, let me state two conjectures about these richer invariants that generalize the conjectures that I stated before. So the first is due to my former student, Katie Gedian, and my colleague, Ben Young, from 2017. So the Orlick-Solomon algebra is equivariantly log concave. So if I take OS of I, tensor OS of I, as a representation of my automorphism group, then that's bigger than OS of I minus 1 tensor OS of I plus 1. Now again, if gamma were trivial, then these are just vector spaces. So the only thing they remember is their dimensions. And this would be a vector space of dimension AI tensor AI times AI. And this would be a vector space of dimension AI minus 1 times AI plus 1. And this would just be the theorem of Adiposito and Katz. This conjecture is a much richer conjecture. And it's not known, I mean, it's known for certain special cases, but it's unknown in many cases. For example, when M is the braid matroid, so the Orlick-Solomon algebra of M is the cohomology of configuration space of endpoints in C, which is acted on by Sn. So even in that case, this is not known. The last conjecture, well, let me remind you of the non-categorical version. So we have this conjecture that the Chow polynomial and the augmented Chow polynomial have strictly interlacing real roots. So I want to reformulate this as a conjecture about something being positive. So suppose I have two polynomials, f and g, where the degree of f is 1 bigger than the degree of g. So I can make something called the Bézout matrix. I take f of x, g of y, minus f of y, g of x. This is anti-symmetric in x and y, so it's a multiple of x minus y. And I divide by x minus y, I get a symmetric polynomial in x and y. And then I just want to take its matrix of coefficients. So that's called the Bézout matrix, or the Bézoutian. And a theorem of Krein and Naimark is that these polynomials have strictly interlacing real roots if and only if this Bézout matrix is positive definite. This is actually really cool. You don't have to know in advance that these things are real rooted, right? If the Bézout matrix is positive definite, that implies that the polynomials are real rooted and that their roots strictly interlace. So now I want to use this to come up with sort of an equivariant version of this conjecture. So if I have two graded vector spaces or graded representations of a group, then I can sort of make polynomials where vi is, the coefficient of t to the I. So these are polynomials whose coefficients are not numbers, but representations of my group. And now I can define the Bézout matrix as before, using tensor product instead of multiplication. And now I'll get a symmetric matrix whose entries are virtual representations of gamma, alternating sums of representations of gamma. And I'm just going to define, I'm going to say W strictly interlaces V if and only if all of the principal minors of this Bézout matrix are honest representations rather than virtual representations. Again, if my group is the trivial group, this is just saying everything has positive dimension. I should have said non-zero honest rather than virtual representation, so that it really generalizes the case of the trivial group. And then conjecture, due to George Nazer and myself, is that the Chow ring strictly interlaces the augmented Chow ring in this equivariant case. So let me just write down one example. So suppose I have the Boolean matroid on the set 1, 2, 3. So 1, 2, 3 is a basis, and that's it. The Bézout matrix looks like this. So the entries, a priori, the entries should be virtual representations of S3. And the irreducible representations of S3 are given by partitions of 3. It turns out that all the entries are really honest representations in this case. So like here, it's the irreducible representation corresponding to the partition 2, 1, plus the irreducible representation corresponding to the partition 3, and so on. And one can check that all the principal minors are honest representations, non-zero honest representations. In fact, I don't really know what to make of this statement, but in fact, all minors are honest representations. This matrix is not just positive definite, it is totally positive. All minors, including the entries themselves, are honest representations. I'm not sure what that means on the level of polynomials. And positive definite means that they interlace. Totally positive is some stronger condition. I have no idea what that should mean, but it seems to be true in our case, even equivariantly. Okay, that's all I've got. Thank you very much.
Thanks a lot, Nick. Questions from the audience?
Hello, can I ask a random question?
Sure.
Okay, so I guess sometime earlier you had this sort of convolution thing. I was kind of curious about something. So it may seem a bit random at first, but hopefully it's, I don't know, not completely random. So there's this identity relating basically like information of the Hilbert-Poincare polynomial, like Hilbert series on like links of simplicial complexes, just like on vertices. So basically information related to a particular like point. If you think about the like face poset of a polytope, and it turns out this is related to some expression like involving the derivative. And the reason I'm asking about this is that this kind of comes up okay, many people have shown something like this related to H vectors of polytopes, but it turns out you can show this using some kind of convolution related argument, like by constructing some kind of convolution on like these like H vectors. I was wondering, like, in the case that these polytopes come from matroid polytopes, is there any like way to explain some analog of this?
Yeah, that I have no idea.
Okay.
Yeah. But it sounds like it might be interesting to look into. Yeah.
Okay.
Question.
Maybe I'll take the chance to ask a question. Can you use this, Nick, to look at, sort of homological algebra questions about the Orlick-Solomon algebra, like it's causality or something like that, or for that matter, causality of the Chow ring, or is that an orthogonal pursuit, would you say?
Yeah, again, I have no idea. I mean, as far as I know, in terms of applications of valuativity, there's sort of two things that come to mind. One is it allows you to do calculations pretty fast for large classes of matroids. And the other is that if you want to prove some formula that you can only prove for realizable matroids, you can often use valuativity to prove it for all matroids. It's some additive formula. I don't know of other applications of valuativity. So yeah, it would be awesome if there were some, but nothing that I'm familiar with.
Dave's got his hand up.
Hey, this is maybe like a little technical question, but in the condition on real rootedness for polynomials, kind of obviously G has to be degree 1 greater than F, and you made that a condition in the theorem, the 9-mark theorem. Is there, what's the analog here? I mean, okay, the dimension of
The analog here?
augmented Chow ring. Yeah, what's the categorified version of that?
Oh, just
Oh, is it just that? I see.
yeah. V goes up to degree D and W goes up to degree
It's a
D,
degree thing. Okay, I see. And following on that, in the example that you gave,
right?
presumably there's some kind of, I mean, I believe this is a true statement. You can translate all of this into some statement about positivity of Schur functions.
Yeah, of course.
Right. So it's something you can check. Is the positivity you're asking for known in any such examples? Say like when you actually have a full symmetric group representation, or it's okay.
I mean, yeah, I think the example of the Boolean matroid has got to be the easiest one.
Yeah.
And
Okay.
it's not known to me.
Cool.
I mean, we've checked it on a computer for small values of various uniform matroids, including Boolean matroids and braid matroids. In all these cases, the group that's acting is Sn, and you know that, of course, we check it using Schur functions on the computer. So so things seem to work, but I don't know of any special case where this is known.
Can I
Thanks.
jump on that Schur function note? So Okenkov had some sort of a conjecture on log concavity that I think was related to Schur functions, but Wayman and Dirksen and Wayman found a counterexample to the conjecture of Okenkov, and I'm wondering if there'd be a way to sort of port that conjecture into matroid theory, and whether, or at least it would be worth looking at in the context of your conjecture.
Right. I mean, I think they're looking at graded pieces of, I mean, sort of weight spaces of representations of symmetric groups, or something like dimensions of weight spaces of representations. So
I don't remember the specifics of it.
I'm a little bit familiar with that conjecture in the examples,
Okay.
but I don't know of a direct connection.
Okay.
Maybe we give the last word to Kumars.
Hi, Nick. Beautiful talk and conjectures.
Thank you.
Just a comment or a question, vague comment question. Is there any connection with logic and model theory? It reminds me of Motivic integration stuff. Maybe one way to approach this conjectures is to look at them, some model theory approach, where if you can prove it for some category, then it's true for all other categories, that kind of.
That's something I really have no idea about, but yeah, that would be exciting.
That's all. Yeah, thank you.
Sorry, may I quickly ask, is the total positivity part of your conjecture, or you think it's just only a coincidence for this simple example?
I guess I'm not sure.
Oh.
I have not yet seen an example where total positivity doesn't hold. But so maybe I should go ahead and say it's a conjecture, but I mean, I don't, I mean, somehow the conjecture here is, you know, the non-equivariant conjecture about strictly interrelated